Good morning. So this morning we'll be dealing with chemical equilibrium. Are we together? Can you hear me? Good morning, class. This morning we'll be dealing with chemical equilibrium. Okay, we should recall that when we're talking about energy changes, isn't it? We talked about enthalpy. Are we there? Yes. In your previous class, you've done enthalpy. Heat changes. Have you done that? No. Not done it. Okay, from our previous knowledge, you know that we've done enthalpy, isn't it? Yes. Then you've talked about spontaneous reactions. Are we there? And there are two factors that affect spontaneous reaction. That is, two factors determine whether a reaction will take place spontaneously or not. In the first place, what is spontaneous reaction? Unaided reaction. That is a kind of reaction that takes place on its own without the assistance of any external factor or external condition. Is that okay? And there are two factors that determine that. That is what? Entropy and give free energy. Are we together? There are two factors, entropy and gives free energy. Entropy is denoted as what? Delta S. And the free energy is what? Delta G. Those are the two factors that determine whether a reaction is going to take place. And what is entropy? That is the degree of disorderliness. Are we together? The degree of disorderliness of a system. And enthalpy can be either negative, the entropy can be either negative or positive. Are we there together? Then the give free energy. The give free energy, what is energy in the first place? Ability to do what? Isn't it? So the entropy, the give free energy can be positive, can be negative, or can be zero. When the gives free energy is positive, the reaction is not going to take place spontaneously. Are we together? When it is negative, the reaction is going to take. When gives free energy is positive, the reaction is going to take place spontaneously. And when it is negative, it is not going to take place. And when it gives free energy is zero, are we together? Which means the reaction is in the state of equilibrium. Are we there together? So therefore, we are starting with chemical equilibrium. How many of you have played on seesaw before? Seesaw. Did you know what is called seesaw? Yeah. Okay, let's say for example, myself, and that's, what is your name? Ikma. Myself and Ikma, we are placed on seesaw. I'm at this edge, and Ikma is on the other edge. What is going to happen? Is she going to fall down? Yes. She will not fall. She will be hot. Yes. If we are both on seesaw, I'm on this side, and Ikma is on the other side. Ikma is going to be up. So what I'm going to, and I want to balance that. Are you with me? What is going to happen? You have to, yes. Is it that I shift forward, or I shift it back forward until we are able to balance? At that time, there is not going to be observable change. Everything is going to be on the same level. At that time, we will say that it is in a state of equilibrium. Are we there together? At that time, we will say that it is on the state of equilibrium. So the same thing is applicable to chemical reaction. When there is no observable change in the reacting particle, then we are going to have chemical equilibrium. Are we together? When there is no observable change in the reacting particles, we have chemical equilibrium. And the equilibrium, the chemical equilibrium can be static or dynamic. Hello? Chemical equilibrium can be static or what? Dynamic. When a system is on the state of rest or is in a statutory position, we say that it is a static equilibrium. Are you with me? And the dynamic equilibrium, that is when the rate of the products and the rate of the reactants are equal. A dynamic equilibrium is when the rate of the reactant is equal to the rate of the product. We say that we have a dynamic equilibrium. Then let's look at the characteristics of dynamic equilibrium. Please write. You don't want to write? If you don't want to write, I can just continue teaching. Okay. Did you understand what I've just explained? Yes, ma'am. Are we there together? Yes. All right, I've talked about dynamic equilibrium, and I've brought you to the scenario whereby we will have a state in which we don't have the condition is not in the state of equilibrium, isn't it? That is when I use seesaw, myself and Awu and Ikma. When we are not in the state of equilibrium, the seesaw is still bending, isn't it? I was down, Ikma was up, until I was able to shift the boat's position, isn't it? And we are able to achieve a state of rest. That is a static, and we remain like that. That is a static equilibrium. Are we there together? So I said dynamic equilibrium. When the rate of the reactant is equal to the rate of the product, we have what? We have dynamic equilibrium. So at times you find questions asking you to say the chemical characteristics of chemical equilibrium or dynamic equilibrium. Are we there together? Are we there? Yes. So one. The rate of reactants must be equal to the rate of the products. Are we there? Yes. The rate of reactant must be equal to the rate of the products. Is it taking? Must be equal to the gift free energy of the gift free energy must be equal to zero. The gift free energy must be equal to zero. Yes, you cannot hear me. The gift free energy. Somebody said you cannot hear me. Must be equal to zero. It is not affected. It is not affected. Number 3. It is not affected. Number 3. It is not affected by catalysts. For equilibrium to be established, number 4. For equilibrium to be established, the system must be closed. The system must be closed. That is, that reaction should take place in a closed system. And what is a closed system? What is a closed system? That is a reaction that is taking place, a reaction in which none of the reacting particles can escape into the environment. That is a closed system. Is that okay? Now, everybody look up. When we are dealing with chemical equilibrium, we'll be making use of this arrow. This, for chemical equilibrium, that is one of the characteristics. It is a reversible, it must take place under reversible condition. That is, it is a reversible reaction. When we say a reaction is reversible, that is, the reaction can go in both directions. Hello? When we say a reaction is a reversible reaction, are we there together? It can go in what? In both directions. That is, the reaction can go forward or the reaction can go backward. And this is the arrow that indicates forward and backward reaction. So in chemical equilibrium, we're going to be making use of those arrows. Are we there together? Are we on the same page? Yes. For irreversible reaction, it is just going in one direction. It is going in one way. So this is the arrow for what? This is the arrow for irreversible reaction. And this one is for reversible reaction. That is the reaction. The reactants can give us products. And the products can in turn give us the reactant. Is that okay? Now, let's look at the factors that affect chemical equilibrium. Factors that affect chemical equilibrium. Are you with me? The factors that affect rate of chemical reaction, we have what? We have temperature, we have concentration, we have pressure, and I also put catalyst there. You can find out that I start my catalyst. Is that okay? So I will get to that. Yes. Surface area. Which one? Sunlight. Those ones are rays of reaction. Now, students make mistakes. When they ask you to list factors affecting chemical equilibrium, you begin to list factors affecting rate of chemical reaction. So there are two different things. Are you with me? The factors affecting rate of chemical reaction deals with product formation, isn't it? Yes. Bond breakage and bond formation. in respect to time. Are you with me? Now we are looking at how they stay on the same level. That is when the reactant is equal to the product. That is what we are talking about in chemical equilibrium. So we are also looking at when, in this case, we are looking at the amount of products that are formed, amount of reactants that are formed when this factor affects that reaction that is in the state of equilibrium. So don't mix them up. Eh? Factors that affect rate of chemical equilibrium. Did I say rate of reaction? Rate of chemical. You said it's wrong. Okay, but I'm talking about chemical equilibrium. Are you with me? Equilibrium, singular, equilibria, plural. Are we there together? So these are the factors that affect them. So what is temperature? It's the degree in your what? Of hotness or coldness of a body. So let's now see how it affects chemical equilibrium. Let's look at the Chatelier principle before I explain this factor. Are you with me? Before I explain the factors, let's look at the Chatelier principle. Are you with me? The Chatelier principle. Who wants to state that? Igma. Yes. The Chatelier principle says that. I should remind you again. Yes. Someone wants to where you are. The Chatelier principle of the equilibrium says that if a chemical contains reaction in equilibrium and one of the factors changes, the equilibrium position will shift, not have the effect. Check this is check. Le Chatelier's principle, she said Le Chatelier's principle says that again. If a system is in a state of equilibrium, yes, and one of the factors is changed, isn't it? Or is altered, the system is going to do what? Shift in such a way to cancel or counteract the effect of that change. Yes. What are we saying in essence? Hello? Are we together? Le Chatelier principle says that if you want to write, let me give you. Le Chatelier principle says that if a chemical system is in a state of equilibrium, and one of the factors involved And one of the factors involved in the equilibrium, and one of the factors involved in the equilibrium is altered. One of the factors in equilibrium is altered. Are we there? The equilibrium position will shift. The equilibrium position will shift. The equilibrium will shift so as to annul, A-double-N-U-L, annul, that is to cancel or neutralize, so as to annul or neutralize the effect, hello, the effect of that change. Are we together? So as to annul or neutralize the effect of that change. Are we there? Is it taking? Hello class, is it taking? So what is the Chatelier principle saying? Okay, let's say for example, as I'm standing here, I'm in a state of equilibrium. According to the Chatelier's principle, and one of you push me to this side, I'm already tilting towards this direction. But according to the Chatelier principle, I'm going to shift in such a way that I will come back to this position, to the position of equilibrium. Did you understand my analogy? Hello, class. Everybody look up, please. Let's assume I am already in a position of equilibrium. Are you with me? This is my system. I'm in the position of equilibrium. And one of you decided to push me. Hello? One of you decided to push me to this direction. Now I'm standing this way. You know I did not balance. Isn't it? My equilibrium position has done what? It has shifted, isn't it? Then this system will react to that change in such a way that I will come back to my original position. Are you with me? Did you understand this analogy? That is what the Chatelier principle is saying. And these factors, if you recall, hello? If you recall that addition or reduction in any of those factors, when you were talking about rates of chemical reaction, is it that it increases the rate or it decreases the rate? Are you with me? So if any of these factors is added or reduced, the system is going to act in such a way that it will cancel the effect of your alteration on that system. Are we there? So let's deal with these factors one after the other, and let's see the effect of the Chatelier principles on them. So let's start with temperature. Are we there? Are we there? Temperature. Temperature. You know we have two types of reaction, isn't it? Endothermic reaction and exothermic reaction. Endothermic reaction is that reaction that does what? That liberates heat into the environment, isn't it? And the endothermic reaction does what? Absorbs heat from the environment. Okay? Now we are looking at effect of temperature. For endothermic reaction, under temperature, For endothermic reaction, endo. For endothermic reaction, increase in temperature, shift the position of equilibrium. Shift the position of equilibrium to the right. Shift, are we back together? Uh, shift the position, shift the what? The equilibrium to the right, thereby favoring product formation. Thereby favoring the product formation. Thereby favoring the product formation. People should note that forward reaction deals with product. Backward is what? Reactant. Look at this arrow. I don't know if you've come across any equation that gives this arrow like this. Hello? Have you seen this arrow before? Yes. So anytime you come across this arrow, it's telling you that this reaction, hello, it's telling you that more product is being formed. That is, the reaction is favoring what? Product formation. And when we add this, look up everyone. Look at that reaction. Look at those arrows. When you have the first arrow, that is when the first arrow is longer to the right hand side, it favors the forward reaction. And the forward reaction is talking about product formation. When the backward reaction is talking about what? Backward formation. Are you with me? So if the arrow is longer to the right hand side, that is, more products are being formed. And when the reaction is longer, tilting towards the backward side, that is, more products are formed. Are we together? Did you understand? You can put it somewhere. So I said, I'm taking it again. For an endothermic reaction, increase in temperature, shift the position of equilibrium to the right, thereby favoring the product formation. Product formation, put in brackets, forward reaction. Are we there? Are we there? I said in brackets you should put what? Forward reaction. While a decrease, that is a reduction, decrease. Yes. While a decrease in temperature favors backward reaction. Backward reaction. Eh? Yes. While a decrease favors backward formation. Hello? Just write what I'm saying. Are you not hearing me? When a decrease in temperature favors backward reaction. That is, the equilibrium position shifts to the left. Equilibrium position shifts to the left. Equilibrium position shifts to the left. And there is more formation of reactants. Is that okay? There is more formation of reactants. Is this okay? Are we back together? Are you with me? Are we back together? Yes. Are we back? So let's look at what the Chatelier principle is saying.
Wow.
Yay! Yes. So listen, according to the Chatelier principle, are you with me? According to the Chatelier principle, if the temperature is increased, are you with me? That is the heat for that reaction has been increased. The system will act in such a way that it will cancel the effect of that heat that is being added to the system. Are you with me? There's going to be a cooling effect. Hello? There's going to be a what? There's going to be a cooling effect. You've added it to the system that, according to the Chatelier's principle, you've added it to that system. Isn't it an increase in the temperature? The position will shift by cooling itself to annul the effect of what? Of the heat that you've added, but that is by cancelling the effect of the heat added. Are you with me? Thereby favoring forward reaction. So that is for exothermic reaction. And for endothermic reaction. And if there is a reduction in the heat, are you with me? If there is a reduction in the heat, there is going to be an heating effect. It is going to the system is going to absorb more heat. you got it now? Endothermic, that is absorption of heat from the surrounding. And endothermic is the release of heat into the surrounding. So for exothermic reaction, yes. For exothermic reaction, increase in temperature, for exothermic reaction, increase in temperature shifts the position of equilibrium. Shifts the position of the equilibrium to the what? To the left.
Change the position of equilibrium
To the left. Favoring backward reaction. Favoring backward reaction. Favoring backward reaction. That is what will happen. More reactants is going to be formed. Are we together?
Yes.
More reactant is going to be formed. Is it taken? Are we together? Are we there? So, a decrease in temperature for exothermic reaction. A decrease in temperature for exothermic reaction. A decrease in temperature for exothermic reaction. The equilibrium position will shift. The equilibrium position will shift forward. The equilibrium position will shift forward, favoring product formation. Are you with me? A decrease in temperature for exothermic reaction will result to more products being formed. Are we there?
Shift forward.
Yes. Favoring the product formation, that is forward reaction. Is it again? Favoring product formation, that is more product is going to be formed. More product is going to be formed. So let's look at effect of concentration. Effect of concentration. Effect of concentration. Effects of concentration. We are looking at those factors that affect rate of chemical reaction, isn't it? Effect of concentration. Effect of concentration. Are we there? Effect of concentration. For a system in the state of equilibrium. Are we together? For a system in the state of equilibrium. For a system in the state of equilibrium. You cannot hear me. For a system in the state of equilibrium. Is it taking?
Yes, ma'am.
Is it are you there? If the concentration of the reactants, if the concentration of the reactants, if the concentration of the reactants if the concentration of the reactants is increased, yes, is increased. If the concentration of the reactant is increased, are you with me? Look at this. We have A plus B to give us what? C plus D. Then we decide to increase any of these reacting species. Hello? If we decide to increase these reactants or any of them, it is going to favor one side than the other. And which side is it going to be which side is going to be favored? It's going to favor the product formation. Hello? If the concentration of the reactant is increased, more product is going to be formed. Are you with me? Thereby favoring the forward reaction. Hello? Are we together? Thereby favoring what? The forward reaction. That is, if I decide to increase the whole of this, are you with me? Or I decide to increase one of it, it is going to favor what? Product formation. Yes. Are we there together? Are we there? Now, if I reduce the products, are you with me? The first one I said increase of the reactants. Now I'm reducing the products. I decide to reduce one of these reactants, one of this product that is being formed. It is still going to favor the product formation. Yes. Yes. Are you with me? Now, yes, I said if the reactant is increased, it is going to favor the forward reaction, that is product formation. If the product is reduced, yes, if the product is reduced, that is decreased, isn't it? It is still going to favor what? It is still going to favor the product formation.
And if the concentration of the product
Is reduced. Are you with me? Hello? Hello, class. Do you understand? Okay. I have A and B to give me what? To give me C and D. An increase in any of these. Let's decide, let's say for example, I've increased this A to 2. Are you with me? Yes. This reaction will act in such a way that more products is going to be formed. Are you with me? Now let's assume. Did you understand that? Is it taken? Now let's assume that I've reduced this one by half. One of the products. One of the products is also decreased. Are you with me? It is still going to favor this forward reaction. Yes, it is still going to favor that forward reaction. Are we together? I have increased. If I increase this, it's going to favor this. If I reduce this, it's still going to favor this. Yes. So let's continue so that you understand. Is that okay? Wow. Oh yeah, it has that rule. Okay. When you take this, it's more than again. Also, if the product, if the concentration of the product, now you will get it. Also, if the concentration of the products is increased, also, if the concentration of the products is increased, you've written that one. Just take this. Also, if the concentration of the product is decreased, is increased. Okay. It will favor backward reaction. Also, if the concentration of the product is increased, are you with me? It will favor backward reaction. That is, it leads to what? More reactants.
I see.
Are you with me? Or a decrease. In the reactants. Or a decrease in the reactants. Or a decrease in the reactants will also favor backward reaction. Will also favor backward reaction. Hello? Are we together? Did we get it now?
Yes.
The first one, I said an increase in the reaction, an increase in any of the reacting particles. Hello? Are we together? Now look at this reaction. We have 1. Let's do it this way. Reactant A is 1. Reactant B is 1. Isn't it? I decide to increase the concentration of the reacting particles. Let's assume I've increased this A to 2. We now have more reactants in there, isn't it? We've added more reactants. It is going to lead to what? More products. Are you with me? Are we there together? At the same time, if we reduce, this one is also 1, isn't it? I've reduced this one to R. Are you with me? It's still going to favor production. Are we there? It's going to favor the forward reaction. And I said a decrease. Are we together? A decrease in the reactants. It will favor backward. You know, initially we have 1 here. I've decreased this one to R. This will favor this. I increase this one to 2. This will favor this. Chatelier, is it understood? Yes. Somebody is still confused. What is your name? Blessing. What is it? Yeah. You are confused. Okay, let me put it this way. Increase or decrease. Increase or decrease in concentration favors forward production, forward reaction. That is more product is going to be formed. If you increase the concentration, more product is going to be formed. if you increase the concentration of the reactant, you will still get more products. Isn't it? If you now decrease from this product, the original reaction, you now decrease from that product again, it will still favor this. Did you get that now? Eh? It's not sinking. So, and I said also, if we decrease this one, it is going to favor, if we decrease this, it's going to favor this. This is backward. It is going to favor this. Are you with me? And if we now increase the product again, it will favor this. Chatelier, did you get it now? Understand? So let's go to 6. Somebody saying no. Yes, you have a question. That is, just understand, that is it. So let's look at another fact. You're saying you don't understand the concentration. I should repeat it again. Increase in the reactant leads to product. Are you with me? Yes. Reduction in the product still leads to more products. Increase in the reactants. Decrease in the reactants leads to more reactants. This one leads to. So let's go to backward reaction. Yes, we will get more of the reactant. That is the backward reaction. Are we together? So let's go to pressure. Now, when we are dealing with pressure, hello? When we are dealing with pressure, we are dealing with gases, isn't it? Pressure does not affect liquid or solid. So the reacting particles, at least one of the reacting particles must be in the what? In the gaseous state. Are we there together? Are we on the same page? I said one of the reacting particles must be in the gaseous state. Are we there? And if we could remember our Boy's law, what does it say? Inversely proportional to the volume, isn't it? Yes. As the volume increases, the pressure decreases. As the volume increases, the pressure what? Decreases. As the pressure decreases, the volume decreases. So this is what is applicable in this case. Are you with me? So we are going to apply what? We are going to apply what is it called? We are going to apply the Boy's law. When we are we back together? So let's take this. Effects of pressure. Effects of pressure. Yes, more is compulsory because pressure does not affect solid or liquid. So pressure of gas. Are you taking it? Pressure of gas. Pressure of gas. Pressure of gas is proportional. Yes. Pressure of gas is proportional to the number of moles.
But please take note of this, that the positive relationship between the consumption and the response is
proportional to the number of mole.
what?
Are you with me?
Yes.
All right. Good talk. Increase in number of mole.
Ma, pressure of gas is directly
I did not say directly.
proportional to the number of
Mole. Are we there?
yes.
Increase in number of mole implies increase in pressure. Increase in number of mole implies increase in pressure. Increase in the number of mole implies increase in pressure. Are you with me? And vice versa. Ah? Is it taking? Full stop. If the forward reaction proceeds, right, please. If the forward reaction proceeds, by decrease, if the forward reaction proceeds by decrease,
Yeah, we can write everything here. Before we move on, we can write
in number of mole, by decrease in number of mole,
since your consumption function, since your consumption is a function of your income. Are you with me? And the income we are talking about is about and your disposable income. Sorry. And your disposable income is why my
I said if the forward reaction proceeds by decrease in the number of mole, put in brackets pressure. Are you with me? Mama? An impulse increase and I don't say and an impulse increase yes, an impulse increase favors forward reaction, that is product formation, favors forward reaction, favors forward reaction. Are you with me? What am I saying in essence? I said an increase in pressure. Are we with me? Are you with me? If you increase the pressure, there's going to be what? There is going to be an increase in the product that is going to be formed. Hello? If you increase the pressure, there is going to be what? More pressure formed. The result. You do not understand. Eh?
No, man.
Yes. Are you with me? An increased pressure favors what? Favors forward reaction. That is, the higher the pressure, the higher the product.
Now come again. The higher the pressure, the higher the product.
Yes. So in the case, full stop.
The higher the pressure.
Full stop. If, are we together? If there is an increase, in the number of mole, if there is an increase in the number of mole,
autonomous consumption. Meanwhile, it was
If there is an increase in the number of mole,
so what they are telling us is that consumption is
if there is an increase in the number of mole, please. Hello, hello. Let's go back to our. I think I've made a mistake. Wait. I said, if the forward reaction proceeds, by what?
Decrease in number of mole.
Okay, decrease in the number of mole, which is pressure. There is an increase in the volume, isn't it?
An impulse increase favors.
Eh?
An impulse increase favors the forward reaction.
Yes.
Wait. Decrease number of mole. It's not about
Wait. By decreasing the number of mole, isn't it? An impulse increase will favor forward reaction. I said, if you decrease, isn't it? You decrease the pressure, the number of mole, isn't it? There's going to be increase in the product, isn't it? Okay, let's continue. In other words, full stop. In other words, high pressure. When high pressure is applied, in other words, when high pressure is applied, when high pressure is applied, the equilibrium position will shift. In other words, when high pressure is applied, yes. When high pressure is applied, the equilibrium position will shift. Will shift. Are you with me?
Yes, ma'am.
To favor the side. With less mole. Will favor the side with less mole, less number of mole. Are we together? Are we there? Look at it. Write this equation. This is what I'm saying. Hello? Let's assume this is the state of equilibrium. There's no need. You know, assume. Look up. Look at the side. Hello? We have the number of moles in the reactant side is how many? 4. We have 4 moles here. And we increase pressure. Are you with me? We increase the pressure here. So the equilibrium position will shift to the side that have what? That have less. thereby favoring which production? Favoring the ammonia production. Hello? Hello? Are we together? Yes. We are not together. Ammonia, 1 mole. Are you with me? I mean, sorry. Nitrogen, 1 mole. Hydrogen, 3 mole. And what it produced was what? Ammonia. Just 2. I wrote that this is how. Are we together? Please change that. Is Na3. Write the equation. So if look at these 2 sides, which one has a less number of moles? The product side. Then we now increase the pressure. When the pressure is increased, are you with me? When the pressure is increased, it is going to favor forward reaction. That is, the equilibrium position will shift to the forward side. Thereby, we will now have large number of what? Ammonia that is being produced. Okay, now I'll be using more. Let's use volume so that it can comply with the what? With the Boyle's law. I'm not going to clean the volume. I'm not going to clean. Yeah. Are you with me? Hello? Hello? We have larger volume at this side, at the reactant side. Isn't it? Are you there? We have larger volume at this side. Isn't it at the reactant side? Then the volume there is what? 2. An increase in the pressure will increase what you are going to produce. This is the original reaction, which means if we increase the pressure, this one has 4, and this one has just only 2. An increase in pressure will do what? Will increase the volume we are going to produce. And that is now complying with what? With Boyle's law. Are you with me? And vice versa. A decrease in pressure will make this to tilt towards this direction, thereby favoring what? Favoring the reactants. That means we are going to have more reactants. Are you with me? Is it taken now? So for production of ammonia, a forward reaction favors that. Then lastly, I put a catalyst, isn't it? What is catalyst? Now, I just heard somebody said speed up. Don't use that word speed up. Please, always use alter. Is that okay? Catalysts are substances that alter the rate of chemical reaction without itself taking part or changing at the end of the reaction. Are you with me? It takes part in the reaction, at least it either lowers it or without itself used up in that reaction. Is that okay? And we should take note that we have 2 types of catalysts. We have the positive catalyst and the negative catalyst. That is why I said you should not use the word speed up. Because speed up, positive catalyst speed up the rate of reaction, while the negative catalyst reduce the rate of reaction. Are we together? Are we on the same page? So for a chemical equilibrium, a system that is in a state of equilibrium, catalyst does not affect them. Hello? But what catalyst does is that it reduces the activation energy, the activation complex. Are you with me? That is, it reduces the time taken for the reaction take place. So whether catalyst is there or catalyst is not there, it will attain the state of equilibrium. But when catalyst is there, it's just going to make it faster. Are you with me? So for what of catalyst, can I clean this?
This is my consumption. So my income, guys, look at it. You understand what I'm talking about now. Let's say my income is 2,000.
So one of the characteristics of a system in equilibrium is that it's not affected by catalyst.
What is left for me to do?
Yes. Let's say, for example, we have this. This is our reactant.
I'm from 3,000. I began to bring 2,000 there. What's the left? Are you with me? So if I say what is my marginal,
Are you with me?
my
And
marginal
this is our activation complex. We have our EA here.
in my income and change my consumption to minus consumption.
Activation energy. So if catalyst is added to a system that is in a state of equilibrium, what is going to happen is that it's only going to lower this. Are you with me? It is not going to affect the state of equilibrium. It has nothing to do with the state of equilibrium. But it is going to affect what? The time it takes for the reaction to take place. It's going to affect the time it takes for the reaction to go into completion. Are you with me? Yes, it's going to bring down the activation complex. Are we there together? So that is that about the factors that affect rate of chemical reaction. So let's look at the importance of Le Chatelier's principle. Is it time?
Yes. Just few more minutes.
I have 9 more minutes.
Yes.
Let's quickly take that. Importance of Le Chatelier's principle. I've explained that it does not have effect on the chemical equilibrium. Only lower the time it takes. Number 1, importance of Le Chatelier's principle. It defines optimum conditions for chemical process. It defines optimum conditions for chemical process. It defines optimum. It defines optimum. Is it taking? Condition for chemical process.
Effect of nature.
Importance, not effects. For chemical process.
Now come again.
It defines optimum conditions for chemical process. 2, reduce undesirable reversibility. It reduces undesirable reversibility.
Everybody look up. Marginal propensity.
Reversibility. Number 3.
And now what?
Number 3. Predict the effect of predicts. Number 3. It predicts the effect of an altered factors on equilibrium. Altered factor on the equilibrium. Yes, altered factor
Please look at this.
on the equilibrium. Of the equilibrium.
Thank you. So, LP.
Are you with me? Are we there together? All right.
Now, guys, look at this.
I've given you 3, right?
Yes, ma'am.
So let's look at equilibrium constants. Equilibrium constants. Equilibrium constants.
Because FPS, what did I say? Equal to. Okay, 0.7 plus 0.3. What is it? Is it correct? Do you understand? Is it correct? Now, move on. Yes, if I say, look at this one. If I say 1 minus N B C, I said it will give us what? FPS. 1 minus what? 0.7.
So equilibrium constants. Are we together? Are we together? Equilibrium constants. The law of mass action says that at constant temperature, if you want to, the law of what? The law of mass action. The law of mass action. Of mass action states that at constant temperature, please don't repeat after me, just listen. Are you with me?
Yes, ma'am.
At constant temperature, the rate of reaction at constant temperature, the rate of reaction is proportional. The rate of reaction at constant temperature, the rate of reaction is proportional to the active masses, of each of the reactants, of each of the reactants, full stop.
To the active masses of each of the reaction.
Yes. Full stop. Is it again? All right. The active mass of the the active mass of the reactant, the active mass of the reactant, the active mass of the reactant is the concentration. Is the concentration of the substance. The active mass of the reactants is the concentration of the substance raised to the power of coefficients. To the power of coefficients. Raise to the power of coefficients. Put in brackets number of moles of that substance. Number of mole in brackets of that substance.
Number of mole, close the bracket.
Yes, I already said in brackets. Are you with me? Number of mole in brackets of the substance in the equation of reaction under study. In the equation of reaction under study. So this is what I'm saying. In the equation of reaction under study. This is what I'm saying. A plus B to give us what? C plus D. Are you with me?
Yes, ma'am.
These are the words. This is the reactant. And this is the what? The product. Are you with me? And these are the coefficients. Are you with me? The small letters are what? They are the coefficients. So this one can be of different numbers. I said raised to the power of the coefficient. Are we there together? So if we now want to apply the law of mass action into this, you already know that this is A. Isn't it? Concentration of A from the definition, please. Are you with me? That is concentration of A, concentration of B, concentration of C, concentration of D. You should take note that this thing means what? Concentration. Are we together? I said raise to the what? The coefficient. So the coefficient of this one is what? A. The coefficient of this one is B. This one is what? This one is what? So equilibrium constant is, that is Kc, is equals the concentration of the product over what? Concentration of what? Reactants. Are we together? Are we there?
Yes, ma'am.
The concentration of the products and the what? And the concentration of the reactant. Level what?
Yes, that's right.
Okay.
Proceed.
So let's just put this. Let's just put this. Are we together? Okay. Let's make this arrow reversible one.
Of course.
So, Kc is equals what? The product is
Sorry, ma'am.
Is it taking?
Yes.
Yes. From here, the products. Okay, sorry. Kc, concentration. Equilibrium of the concentration. Is that okay?
Yes.
Are we together?
Let us write this.
Now where Kc is equilibrium constant. Are you with me? And we also have Kp. Hello? When the reactive particles are in gaseous state, we make use of what? Kp. That is what? The pressure. When the reactive particles are in the gaseous state. So instead of us using this, are you with me? Are we there? So, for a system that is in the gaseous state, if the reactive species are in the gaseous state, are you with me? Instead of using this concentration, we use P, isn't it? Like the formula, products over what? Over reactants. Are we there? So it's going to be Kp of the reactant. This is the equation of the reaction, isn't it? But in this case, they are all in gaseous state. So it's going to be Pc, capital letter C. Are you with me? Times what? PD over what? A plus B. P.
How are you multiplying those?
You multiply this one. We multiply.
Yeah, you are right, because you wrote.
Yes. Now I'm using P. It is not in their concentration. Are you with me? Then we put the coefficient upward. So the coefficients here is B and A. Hello?
Hi.
Is it taking?
Yes, ma'am.
Are we there?
Yes, ma'am.
Hello, class. Are we together?
Yes, ma'am.
So let me give you an assignment.
Thank you, ma'am. Thank you, ma'am.
Check. Como eu ando,
Are you with me? Calculate. Assignment. Calculate. A. Equilibrium constant.
How you say calculate?
Yes. For the reaction. For the reaction below. For the reaction below. Let's take the question before I give you the reaction. For the reaction below. At 45 degrees Celsius. At 45 degrees Celsius. Are you with me?
Yes, ma'am.
B. Equilibrium constant for backward reaction. Equilibrium constant for backward reaction.
Sorry, ma'am. The calculate
Yes. D. The equilibrium constant for backward reaction. Are we there together? Okay. Given that, yes, given that the partial pressure, of hydrogen gas, that just write H2, hydrogen gas. Are you with me?
Yes, ma'am.
Iodine or iodine. Yes, iodine gas and hydrogen iodine. That is H2, I2, and HI. Yes. Are you with me? Are you with me? Iodine 0 points. And iodine. Listen please. Given that the partial pressure of hydrogen gas, iodine gas, and hydrogen iodine is 0.065 is 0.065 atmosphere. You don't write atmosphere, right? ATM. Comma is 0.45 ATM. That is another word. First one is 0.065 ATM, comma 0.45 ATM, comma and is 0.245 ATM. 0.245 ATM, respectively. Full stop. From your answer. Deduce which of the reaction is favored. From your answer, deduce From your answer, deduce which of the reaction is stable. Hello? Have a nice day.
Let's reaction below. Sorry. Reaction below.
That's right. Yes.
Settle down. Settle down. Yes, ma'am. Are you through? You are just writing the reaction. Where, please? She will write it. Hello, just come out when she through. All right, sir.
I don't see extra coded.